Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about this interesting problem. So let's get started. Alright, let's first read this problem. The problem says we are given an array of n non-negative integers representing elevation map of bars where the height and width of each bar is 1. And here our task is to compute how much water it can trap after raining. So before we talk about the solution, let's understand this problem step by step. So the first thing is given as our array contains only non-negative integers. It means we will get 0 or numbers that are greater than 0 in the array. And the second thing is given as elevation map of bars. What does it mean? Map means here meaning of map of bars is where to place the bars, at what position we have to place the bars. And elevation simply means up to what height we have to raise the bars. Okay? And the height and width of each bar is 1. It means we can assume that it is a square bar, so that we can put bar on top of each other. Okay, so I hope you understood the problem. So let's see few examples. Let's see this first example. Here the elevation map is given as 2, 0, 2. It means at position 0 we have to raise bars to height equals to 2. So we have done like this. Okay, at position 0 we have to place 0 bars, and again in position 2nd we have to again raise the bar up to height 2. Okay, now after rain how much water it can collect? As you can see that on first bar we cannot collect any water, on last bar also we cannot collect any water. The reason is pretty simple. To collect some water we need something on the left side or right side to support that water or hold that water. And if you try to collect water on top of these two bars, it simply spills from the bar and fall on the ground. So that is why we can only collect water at position 1. And how much water we can collect here? 2 units of water, right? 1 and 2, because here there are 2 boxes, so the output of this input is 2. Let's see next example. Here you can see that the elevation map is given as 3, 0, 2, 0, 4. So we have to place 3 bars at position 0, then 0 bars, then again 2 bars, then again 0 bars, and then 4 bars. Now how much water we can collect between these bars? On first and last bar we cannot collect any water. On position 1st we can collect 3 units of water. Why? Because the minimum height of bar is 3 here and here it is 4. And if we try to fill water above this level, it will simply overflow, right? So at position 1 we can collect 3 units of water. At position 2 we can collect only 1 unit of water, and on position 3 we can again collect 3 units of water. So the total unit of water we can collect here is 3 plus 3 plus 1, that is 7. That is why the output of this input is 7. So we understood this fact that to collect water we need some support on the left and the right side of the bar so that we can collect the water. So I hope now you have a good understanding of this problem. So let's pause this video and think about an algorithm to solve this problem. Alright, let's talk about the brute force approach to solve this problem. And here we have observations to be made. Let's say the elevation map is given as 4, 2, 0, 3, 2, 5. According to this elevation map, the final setup looks like this. We have 4 bars here, then 2, then 0, then 3, then 2, and then 5. how much water we can collect between these bars. Obviously, on the first bar we cannot collect any water, and on the last bar we cannot collect any water. We can collect water only between these two bars. Okay? So on position 1 we can collect 2 units of water. On position 2 we can collect 4 units of water. On position 3 we can collect only 1 unit of water, and on position 4 we can collect again 2 units of water. So the total units of water we can collect is equal to 9. Okay? Now what if we are given an elevation map like this 1, 2, 3? In this case we cannot collect any water, because as you can see that on the left of this setup we do not have any bar that is higher than this bar. So if we try to store or trap water here, it will simply spills on the ground. So that is why we cannot collect water if we are given arrays like this. And in this array the elements are simply arranged in increasing order. Let's see the next example. What if we get array like this, and in this array elements are arranged in decreasing order? So here also we cannot collect any water. The reason is same, that on the right side we do not have any bar that is higher than this bar. So it means we do not have any support on the right side to hold the water. That is why we cannot collect any unit of water with this arrangement. Okay? So after observing all these examples, we can learn few things, and that is, first thing is we cannot store water on top of leftmost and the rightmost bars, right? And second thing we learn from these observations that we need left and right support to collect the water. Okay? It means we can only collect water between 1 and n-2 elements. Okay? Because on top of these two bars we cannot collect water, so we can collect water between these and these bars only. So let's use this learning and implement an algorithm to solve this problem. So here is the idea. The idea is pretty simple. We have to traverse an array from 1 to n-2 elements. Okay? And for each position we have to find maximum height to the left and the maximum height of the bar to the right. And then we have to find minimum of both the height. After finding minimum of both the height, we just have to subtract the height of the current bar to get the amount of water we can collect at particular position. And then we simply have to add all the computed values to get the total water we can collect with this setup. Let's understand this with this example. So here on first bar we cannot collect any water. On second bar we can collect any water. So what we do? We simply find the maximum height on the left, that is 4, and maximum height on the right, that is 5. And then we find the minimum of both the two heights. That comes out to be 4. It means we can collect water up to 4 levels. But on this position we already have 2 bars placed, so we have to subtract this. So 4 minus 2 is going to be 2. So at this position we can only collect 2 units of water. So far so good. So let's see the implementation of simple approach. Here we have a function trapping rainwater, and this function is taking array as input. In the first statement we are getting length of array. In second statement we are initializing total units is equal to 0. And this variable keep track of total units of water we can collect so far. Okay. Then we are running a loop from I equal to 1 till less than n-1. Correct? And inside this loop we are again initializing two variables Lmax and Rmax. It means the leftmost maximum height and the rightmost maximum height of the bar. It means this variable keep track of leftmost maximum height of the bar and the rightmost maximum height of the bar. And then again we are running a loop from I-1 till 0. It means for a particular position we are going left of it to find the leftmost maximum height of a bar, okay, and store it in a lmax variable. And in the second loop we are going right of particular position to find the rightmost maximum height of the bar. That is why we are running loop from I-1 till 0 and then I+1 till n-1. In this loop we are going left of the position, and in this loop we are going right of the position. After computing lmax and rmax, we are using this math.minimum function to find the minimum of both the heights and subtract the height of the bars at that particular position, and simply adding to total units. So this is how this function will iterate to all the elements of the array and compute total units of water we can collect at that particular position. And after this for loop we are simply returning the value of total units. So this is enough for this function. Now let's dive into this function and see how it actually works. So here the elevation map is given as 420,325. We initialize our total units as 0. We execute this code and our loop begins. In first iteration the value of I is 1 because we are starting from first position till fourth position. The value of left maximum and RM maximum is 0. Then we compute the left maximum for position 1 and R maximum for position 1. We get LM is equal to 4 and RM is equal to 4. Means before this position the leftmost maximum height of the bar is 4, and after this position on the right side the maximum height of the bar is 5, as you can see here. And after computing Lmax and Rmax we are simply computing the minimum of both the values, that is 4, and subtracting the value of the bar itself. So 4 is the minimum value, 2 is the height of bar, 4 minus 2 is equal to 2. So we compute the total units of water we can collect so far is equal to 2. Moving to next iteration. In next iteration the value of I becomes 2. We again initialize LM and RM is equal to 0. We compute the value of LM and RM is 4 and 5. Minimum of both the value is 4. Now total units is equal to previous total units plus the minimum of LM and RM minus height of bar, that is 0. It comes out to be 6. Okay, so total units we can collect so far is equal to 6. Moving to next iteration, the value of I becomes 3, LM is 0, RM is 0, and we compute LM is equal to 4 and RM is equal to 5, and the total units comes out to be previous total units plus 4 minus 3, that is equal to 7. In next iteration value of I becomes 4, LM is equal to 0, RM is equal to 0, LM and RM, then we are computing value of LM is 4 and RM is 5, and the total units comes out to be previous total units plus 4, that is the minimum of LM and RM minus the height of bar. It comes out to be 9. So the output of this input array comes out to be 9. It means we can at max collect 9 units of water between these bars. So far so clear. Now talking about the time complexity, how many times our outer loop is running. So we are running outer loops approximate n times. And what about inner loops? Although we are running 2 loops, but we are not running these 2 loops more than n times, because in first loop we are going left of a position, and in this second loop we are going right of the position. So in total we are running loops n time. So the overall time complexity comes out to be big of n square, because we have a nested loop here, and in nested loop we simply multiply the time taken by both the loops. And what about the space complexity? We are not using any extra space other than few variables and the input array. So the space complexity comes out to be theta of 1. So this brute force approach took big of n squared time and theta of 1 space to solve this problem. This is the question we ask ourselves after solving any problem, that can we do it better? Can we reduce the number of iterations used in this approach? Can we solve this problem in less time complexity? Do we have any other approach to solve this problem? So do one thing, let's observe the given array once again and think about a solution that can solve this problem in big of n time. Alright, let's talk about the efficient approach to solve this problem. The idea of efficient solution is pretty simple. In this idea, what we do, instead of finding Lmax and Rmax for each position, what we do, we simply pre-compute all the Lmax and Rmax in advance, and then we reuse the values pre-computed by us. So to accomplish this, we create two arrays, Lmax and Rmax, and in this array we store all the pre-computed values into this array. So this is the idea for efficient approach. Now let's see the implementation of this efficient approach. So here we have function trapping rainwater, and this function is taking array as input. The first statement is just getting the length of the array. In second statement, we are initializing a variable total units to 0, and then we are creating new array of size exactly equal to the given array, and then we are copying the first element from the given array to this new array, because for position 1 the Lmax remains same as the first element, and then we are running a loop from 1 till less than n, and for each position we are finding leftmost maximum height of the bar. This is how we are creating Lmax array. Now after computing Lmax array, we again going to create new array for Rmax, and here we are storing the last element to the last position of the Rmax, because here we are going to compute the rightmost maximum height of the bar. So we are going to traverse this array in reverse order. So that is why we are running this loop from n-2 till greater than equal to 0. So on this position the Rmax remains the 5, and then we move to next position. So for this position the Rmax is going to be 5, for this position also, and so on and so forth. So this is how we are computing Lmax and Rmax for each position. After computing Lmax and Rmax, we are again going to run a loop from k equal to 1 till n-1, and inside of this loop now we already have Lmax and Rmax, so we can easily compute the minimum of both the values and subtracting the values of bars present at that position. Okay, and this is how we get the total units of water we can collect at a particular position. And in the last, we are simply returning the value of total units variable. So this is enough of this function. Now let's quickly dry run this code and see how it works. So the elevation map is given as 420325, and we initialized a total units variable to 0. First we are going to compute all the Lmax and Rmax of all the position. So it comes out to be 444445, and Rmax array comes out to be 555555. Okay, so you can see that if I consider this position, the leftmost maximum height for this position is 4, and the rightmost maximum height of bar for this position is 5, right? So when we execute this code, our loop begins. In first iteration the value of I is 1, so at first position the Lmax and Rmax is 4 and 5, and the minimum of Lmax and Rmax is 4. So total units is going to be previous total units plus minimum of both the values minus the height of bar at this position. It comes out to be 2. In second iteration the value of I becomes 2, so total units so the total units is going to be 2 plus minimum of both the Lmax and Rmax, that is 4, minus the size of bar at this position, that is 0. So 2 plus 4 is 6. So far the value of total units is 6. In next iteration, the value of I becomes 3. The total units is going to be 6 plus 4 minus 3, that is equal to 7. In next iteration, the value of I is 4. Total units is going to be 7 plus 4 minus 2, that is equal to 9. So for this particular setup or this elevation map, the output comes out to be 9. It means we can collect total of 9 units of water between these bars. So far so clear. Now talking about the time complexity of this function, here we are running loop n times, then again we are running loop n times here, and again we are running a loop n times. So n plus n is going to be 3n. And in asymptotic analysis, we generally do not care about constants and coefficient of higher order terms. So we simply ignore 3. So the overall time complexity of this function comes out to be big of n. Now talking about the space complexity, as we are using two arrays to pre-compute Lmax and Rmax, it means we are using n space to store those values. So the space complexity for this solution came out to be big of n. Great. So before we end this video, let's have a quick recap of what we have done so far. So we were given a problem. In this problem, we were given an array of elevation map, and our task was to compute how much water we can collect between those bars. To solve this problem, we saw the brute force approach. And in this approach, the time complexity came out to be big of n square, and the space complexity came out to be theta of 1. Then after some observation, we saw the efficient approach. And in this efficient approach, the time complexity came out to be big of n, and space complexity came out to be big of n. Because in efficient approach, we were using some arrays to pre-compute the values of Lmax and Rmax. Alright, so by now, I hope you understood this problem really well. So this is it for this video. Thanks for watching. See you in the next video.